Welcome back. We are in the second section of Chapter P. This one is about tree diagrams and Bayes' rule. Both of these, so the reason that these two seemingly very different things are together in this chapter is because they're both dealing with conditional probabilities. We're going to focus on Bayes' rule first, then swing back and talk about tree diagrams. Before we can talk about Bayes' rule, we need to talk about something called the law of total probability. We're going to use this in our calculations when we talk about Bayes' rule. So the law of total probability states let A1, A2, all the way to AK be mutually exclusive and exhaustive events. Then for any event B, the total probability of B can be broken down like so. Notice we're using the multiplicative rule over and over and over again there. So it comes down to that the total probability of B is the sum as I goes from 1 to k of the probability of B given A sub I times the probability of A sub I. And just a reminder, what does mutually exclusive mean? It means that that set of events has nothing in common. And exhaustive is a new word for us. What it means is that set of events, if you put them all together, it makes up the sample space. So that set of events has accounted for all possible outcomes. We'll do an example. In this example, we're interested in spam emails. So an individual has 3 email accounts. 70% of their messages go to the first account and 1% of those are spam. 20% of their messages go to the second account and 2% of those are spam. 10% of their messages go to the third account and 5% of those are spam. So that's the setup there. We know how many go to each account, and of those in a given account, how many are spam. So we want to know what's the probability that a randomly selected message from any account is spam. We're going to go ahead and just write down what we know. So we know that the probability that a message goes to account 1 is 70%. We know the probability that a message is spam given that it was from account 1 is 1%. We know the probability that a message goes to account 2 is 20%. We know the probability that a message is spam given that it was from account 2 is 2%. We know the probability that a message goes to account 3 is 10%, and we know the probability that a message is spam, given that it was from account 3, is 5%. So that was just me rewriting those 6 statements as 6 probability statements. And this is an important thing to practice. So being able to translate from words to probability statements or from probability statements to words is a good skill that you need to know. So it's something you will be tested on both explicitly and implicitly. So make sure you can practice that. Also note that I chose my own symbols here, and that's totally fine. You're able to choose your own symbols. Just if you're going to choose symbols that aren't super obvious, make sure you explain them. So for example, instead of A1 for account 1, if I decided to use W, I should write that here somewhere because that wouldn't be clear to the reader. So then I can just put that all together in the law of total probability. So the probability of being spam is 0.01 times 0.7 plus 0.02 times 0.2 plus 0.05 times 0.1, or about 16%. So probability that a randomly selected message is spam is 16%. And the whole point of this law of total probability thing is that you're accounting for all the possible scenarios, right? So we know that messages can be spam in account 1, they can be spam in account 2, and they can be spam in account 3. So we broke our total probability into those 3 pieces. Now we can talk about Bayes' theorem. Again, Bayes' theorem starts off with that set of mutually exclusive and exhaustive events, A1 through AK. And now we've got a second event, B, and we're going to stipulate that the probability of B has to be greater than 0. That's because probabilities need to be positive, and we don't want it to be 0 because we're going to divide by it. So then that tells us the probability of a sub j given b is equal to that. So first, that was just the definition of conditional probability from section 1. Then to get to this next part, we expanded, and we said the numerator can be expanded using the multiplicative rule from section 1, and the denominator can be expanded using the law of total probability from the last slide. So Bayes' theorem just gives us a way to rewrite the conditional probability. And just a thing about notation here, because the notation can be a little tricky, a sub j means I'm selecting a specific a. So say a sub j could be, a sub 10. And then notice on the bottom, in the denominator, I don't have j anymore, I have I, because in the numerator, a sub j is one fixed a. We're looking at one a. But in the denominator, we're accounting for all the scenarios, so we're still adding from 1 to k. So that's why there's i's in the denominator, but there's a j in the numerator. And Bayes' theorem, as I've written it here, I've written the kind of general, maybe more complicated form that allows you to have as many a's as you want. We're going to simplify this and say we've got one a. I mean, really, we've got two, as you'll see, but we're just going to say we have a and b, and we want to know what Bayes' rule looks like. So this is the one that your book focuses on. So the probability of a given b, again, there's the definition, and then we expand. So this is expanded into the probability of b given a times the probability of a over the probability of b given a times the probability of a plus the probability of b given a complement times the probability of b given a complement. And where that came from was we know that there are two possible scenarios we need to account for, a and not a. So that's why we have a and a complement in the denominator. And again, you can do this for however many a's as you want, but we're going to focus on just having two scenarios to keep it simple. This was created by and named for Reverend Thomas Bayes. He is a very well-known statistician, and this is actually a very big deal in statistics. So Bayes' theorem is the foundation for an entire paradigm of statistics called Bayesian statistics. In this class, we focus on something called frequentist statistics, but there's a whole nother, side to statistics out there that if you go on to take some graduate stats classes, you will most likely run into. We'll do an example, and I'll say Bayes' rule is one of the trickiest things in this chapter, so definitely make sure you understand the example in the slides and the example in the homework. It can be tricky to wrap your head around at first. So just practice it a little bit, and then let me know if you have any questions about this section. So in this example, I'm getting married, and I'm doing it on July 14th, and I'm doing it outside. So I'm very interested in knowing whether or not it's going to rain. I know that in recent years it has only rained about 5 days out of the year where I'm getting married. And I also know that the weatherman has predicted that it's going to rain that day. Not great. And I know that when it actually rains, the weatherman correctly forecasts rain 90% of the time. And when it doesn't rain, he incorrectly forecasts rain 10% of the time. So I want to use all of that information to find the probability that it will rain on the day of my wedding. I'm going to start by giving some notation here, because again, my notation isn't clear, so I should write it. A1 is that it rains on my wedding day, A2 is that it does not, and B is that the weatherman predicted rain. Now I'm going to write down what I know in the form of probability statements. So I know that the probability that it's going to rain is 5 out of 365. I got that from the statement, it rains 5 days out of the year. So if it's raining 5 days out of the year, that means it's not raining on the other 360, so the probability that it doesn't rain is 360 out of 365. And the probability that the weatherman, so we said when it rains, he correctly predicts that 90% of the time. That's the probability of B given A1. We said when it does not rain, he incorrectly says it's going to rain 10% of the time. That's the probability of B given A2. So especially these conditional probabilities really focus on being able to translate to and from probability statements. So now I've got all the pieces and I want to put them together. Using Bayes' rule, I get that the probability of A1 given B, which, let's pause, why is that what I'm interested in? Well, I know that the weatherman has predicted rain, and I want to know if it's going to rain. So the way that you would read this is, given that the weatherman has predicted rain, what is the probability that it's going to rain? So given B, what is the probability of A1? Or what is the probability of A1 given B? So putting things together, that is 0.014 times 0.9 divided by 0.014 times 0.9 plus 0.986 times 0.1, which is about an 11% chance. So there's an 11% chance it will rain on my wedding day, given that the weatherman said it would. And as an update, it didn't rain. So it was a wonderful sunny day. It rained the day before and the day after, but it did not rain the day of my wedding. So next up, tree diagrams. I'm going to give you a few statements about tree diagrams, then we're going to do an example that will make it make more sense. So bear with me for these next 3 statements. The initial set of branches show the probabilities from one set of events. The next set of branches show the conditional probabilities, conditioning on that first set of events, aka the initial branches. If you multiply along a set of branches, you're technically using the multiplicative rule, and so you're going to end up with a joint probability. So here's our example. Suppose a regional airport is serviced by 2 airlines. We have airline C. It runs 70% of the flights, and it's late 20% of the time. We also have airline D. It runs the rest and is late 10% of the time. So let's make a tree. First up, I want to know what airline is a flight from. So is it from flight C or D? 70% went to C, 30% went to D. Now that I've selected an airline, I want to know if it was late or not. So for airline C, I know 20% of them are late, 80% of them are not. For airline D, I know 10% are late and 90% are not. And then maybe I want to know what is the probability that a flight is late and from airline C. I multiply along a branch. So that would give me 0.14. And I can do that for all of the sets of branches. So let's answer a question here. What proportion of flights at this airport are late? So we know that that would be the probability of being late. It's the probability of being late and from airline C plus the probability of being late and from airline D. I can expand those using the multiplicative rule and then do the math. But I could completely ignore lines 2 and 3 here of my work because it's already been done for me over in the tree. I know that the probability of being late and from airline C is 0.14, and I know the probability of being late and from airline D is 0.03. So this overall probability, you just add the two, it's 0.17. So it's a 17% chance. And often, occasionally I will ask you to make a tree diagram explicitly, but usually tree diagrams are just something that you can use to help yourself understand the problem. It's not something you necessarily have to use, but they're a very helpful tool. And if you go on to take data science, you'll see something called the decision tree, which is similar to this. So they are useful. So that brings us to the end of section 2. So I will see you next time.